Okay, Riemann sums and definite integrals. Riemann generalized the rectangle limit process to include any function. So he also has right rectangles, left rectangles, midpoint rectangles, trapezoidal approximations. We're just probably going to concentrate on right rectangular approximations, and eventually we're going to hit the limit as n approaches infinity. We're going to hit that more than anything else today. So first couple things I want to look at is the basic setup. If I have some function y equals f of x over an interval from a to b, then I need to do a couple of things. For n subintervals, which we're going to let approach infinity, we're going to do b minus a over n. This is going to be delta x, which is going to be your basis for x substitution, and it's going to be the width of the rectangle. Okay, these heights, these bases for substitution, I'm going to call delta xi because that's basically in the part where it comes from. So I want the limit as n approaches infinity, and then I need the summation formula I equals 1 to n of the width, which in this case is b minus a over n, times the function evaluated at b minus a over n I, because each particular one plus 2 by b minus a over n's plus 3b minus a over n's plus 4b minus a over n's. Eventually, those are all going to be different heights that are going to creep into this particular bit. So let's take a look at an example just so you can put some numbers to it. So function y equals 4 minus x squared over the interval from 0 to 1. So b minus a over n is 1 minus 0 over n, and this is 1 over n. This is equal to delta x. I should have wrote that. This is equal to delta x. So summation, limit as n approaches infinity, summation 1 to n of the width, 1 over n of each rectangle, times the quantity, 4 minus, and then in place of x here, I put I over n, which is again delta xi, and I square it because that's just part of the formula. So as a definite integral, we would write this. This is the same thing as the definite integral from 0 to 1 of 4 minus x squared dx. And we will look at more of these later, but I will keep writing these definite integrals so we can see the tie-in. What if we don't start at 0? What do we do? Well, let's say we start on the interval from 1 to 2, same formula that we looked at before, same function. So again, 2 minus 1 over n is 1 over n, which is delta x. This is the width and basis for substitution. So the width still goes in the same place. Still n approaches infinity, still the summation from 1 to n. Width 1 over n times the quantity, 4 minus. Now here's the part. Instead of just I over n, we have to put in the starting point first. 1 plus I over n quantity squared. Okay, we have to add starting with the lower bound. Now, what would we have to do to this if we were to solve it? I'm not going to go crazy over this math, but if you need to take a minute or two and look at this, this is just FOILed. After I FOILed, I just did some distribution. I went ahead and take a look at the summation by parts, bringing the n cubes outside. I put in the summation formulas that are straight from the book, and then I looked at the limits as n approaches infinity, and I worked this out, and this is the answer for this area. Literally, the answer is exact area is 1 2/3 under here. And the definite integral is the integral from 1 to 2 of 4 minus x squared with respect to x. What if the interval is longer? Okay, so I went from -1 all the way to 2 here. So one of the main differences is delta x is now 3 over n. 2 minus minus 1 is 3. So now this is the rectangle width, and it's still the basis for that substitution too. So again, limit as n approaches infinity of 1 to n, the width, 3 over n, times the summation of all these heights. This would be 4 minus, again from formula 4 minus, and then in place of x squared, starting point again, -1, plus, and in this case, delta xi is 3i over n. Still looking at quantity squared, still from the formula. Not going to go ahead and bore you with the math at this point in time, but I'm also going to say that this is -1 to 2 of the definite integral 4 minus x squared, and I should have wrote a dx here. All right, let's talk about definite integrals, basically. They represent numbers. However, at the same point in time, definite integrals talk about area between curves and the x-axis. So some ideas and properties I wanted to get across here. We drew a square here with area 6, a triangle with area 2, and another triangle with area 6 here. So if we look at definite integrals from 0 to 2, okay, the integral from 0 to 2, definite integral of f of x is just equal to 6. Literally, it's the area underneath the curve. All right. From 2 to 4, f of x is -2. Anything underneath the x-axis, the area slash, I know it's weird to say area is a negative. It's really not the case, but the definite integral comes up as a negative. Anything below the x-axis, the definite integral is represented by a negative. Okay. Therefore, some sort of addition property holds true. So if I wanted to go from 0 to 4, what I would look at is the integral from 0 to 2 plus the integral from 2 to 4, the ones we just did, or 6 plus a -2, and that's 4. We can add results and we can add limits. If you happen to flip one over backwards, so if you happen to start with the lower bound being your higher x value and the upper bound being your lower x value, what it does is it reverses your value. So instead of 2 to 4 f of x being -2, 4 to 2 f of x is actually +2. If you reverse the upper and lower bounds, the limit multiplies by -1. Okay. Same idea from 0 to 4. You can see that this limit is also reversed. And if we go from 0 all the way to 7, we can add all three of these areas up. 6, this would be represented again as a negative, and this is 6, so this 2 positive 6 is -2 is going to be 10. And that's enough for definite integrals and Riemann sums today. Thanks.